always found it a little amusing when someone tells me they're taking a non-calculus based physics course, because physics is always calculus based. The only non-calculus based description of the universe is church, and that's a different thing. Although sometimes physics exams lead to a lot of prayer, so maybe they're more related than I think. Anyway, what they really mean when they say a non-calculus based physics course is that they're not using calculus. They are just memorizing the equations that they need to solve the problems that they want to solve. But really, deep down, it's all calculus. So I thought we would look at calculus at this very early stage of just thinking about position and velocity. So let's start by thinking of our chalk moving along the x-axis at a uniform velocity. We can plot the position versus time, and we know it'll look like that is a straight line. You can also make kinematics plots of velocity. We can plot the velocity versus time. Everywhere you go here, the instantaneous velocity is the same, so it would look like that, just a flat line. So now let's see. The idea of calculus is that these are related. So one way you can go from one to the other is you can go this way. And you go this way by taking a derivative, which we have talked about. We know that the average, no, I just want to do the instantaneous velocity, is the derivative dx dt. Or if you're uncomfortable with calculus, you can think of it as the slope. Everywhere you go here, the derivative, say here, if we come down, the derivative there is equal to the value there. If we come over here, the derivative, you can tell, is the same because it's the same slope, equal to the value here. And there is the same. Everywhere you go, the slope is the same, the derivative is the same. That's why the velocity plot is flat. But you can also go the other way. That's another important idea of calculus. We can go from there, this plot, up to this plot. So we go this way with an integral. So the formula here you would use is you would say the displacement. When you go this way, you got to think of a difference in two places. The displacement, and I'll say from A to B, and let's go ahead and just call these A and B, is equal to the integral. That's really a big S because integrals are really sums. That's like an old-timey S. This integral from A to B of this velocity dt. And if you're familiar with integrals, you know what you would do. You would put in whatever the function is for the velocity, some function of time, and you would integrate. If it's a polynomial or an exponent or a sine, all those tricks is what you learned in calculus. And if you're not familiar with that, also if you're uncomfortable with calculus, you can also think of this as the area under the curve. That's sort of the geometrical interpretation. And what it basically means is if we want the the displacement from there to there, this would be xa and this would be xb. The difference there is equal to the area under the curve there, which you could get from the integral. So you can actually go both ways. What does this have to do with all those equations you memorize? Right? So this really is the fundamental physics. This is always true. This is really the definition, basically, of velocity. But the equations you memorize are special cases. So let's think, what if we applied the special case of constant velocity? Which is what we've plotted here, constant velocity. We could look at this and say, well, if the velocity is constant, we know that the instantaneous, we know that the average velocity between any 2 points is equal to delta x, the displacement between those 2 points over delta t. But we know that the average and the instantaneous velocity are always going to be the same. So we'll just say equals that equals dx dt. As long as that line is flat, any interval, any point, the velocity always comes out the same. So we can kind of say, actually, you could say the instantaneous velocity is equal to this delta x over delta t if you pick 2 points. So let's look at it more then. I'm going to drop the vector notation at this point and just say that v is equal, let's see, how do I want to write this? V, is equal to the delta x, the displacement, is x minus x naught, from where you started to where you went, over t minus t naught. Well, t naught is almost always 0. Right? We always think of the origin of time as 0. X naught sometimes will give an actual x naught, so we'll leave that in the formula for now. But you can see what this turns into with some algebra. The t comes up here, it's v times t. You have x equals v times t, and then bring the x naught over, and you get x equals x naught plus v times t. And that is one of the basic early kinematics formulas that you will memorize when you do kinematics. You're really memorizing all the calculus for the case of constant velocity. Let's look over here. What if we have constant velocity with the integral? Whoops, I didn't mean to cross it out. Let's see, that is saying delta x from a to b. Well, that would be kind of like going from, x naught to some position x. So that would be x minus x naught equals, and then we can just go with the geometrical interpretation of the integral. It's the area under this curve. Well, the area of a rectangle is length times width. So what is the dimension this way? We can call that the length. It is, it's how high it is, it's v, right? So that's v. And then the width is from t naught to t. Is this delta t? Well, t naught we usually just call 0. Call that one 0. It's really just how far it went, t. And there you can see this one as well. You bring the x naught over and you get the same thing. X equals x naught plus vt. Standard equation. So all the equations you memorize in kinematics are special cases. These are special cases of constant velocity, and then soon we'll be talking about the special case of constant acceleration. Those also you can take straight from calculus.